Hi everyone, thanks for joining us. Good afternoon to those in the Bay Area and good evening or good time of the day to anyone watching from around the globe. I'm Nachiket Girish and this is my friend Dhruv Punjabi and we are here to talk a bit about physics.
Hi, everyone. I'm Dhruv. Great to see you all here today. Nachiket and I are third years studying physics at UC Berkeley, and we're here to talk about two major theories in physics, quantum mechanics and general relativity. And we do have quite a bit to cover. So, just for the betterment of everyone else, I think we'd really appreciate it if you could hold off any questions you have until the end, because that way we'll be able to answer everyone's questions faster. We do appreciate that. Thank you.
And as a disclaimer to any card carrying physicists in the audience, we apologize for the superficiality of our knowledge. And to any students like us here, we hope you enjoy learning about something interesting with us. So when we just started about dreaming about becoming physicists, the grand unification of forces was the one topic we kept encountering in our excited readings of pop science. Pop science was back then my only window into the kind of physics I knew I wanted to do in the future. And so even before I knew how to juggle kinematics equations properly in school, I was reading articles about gravity and quantum mechanics and general relativity without actually knowing what those things really are. So for those of you who might be thinking about becoming physicists yourself in the future and keep hearing about quantum mechanics and GR and unification, we thought we could briefly go over what these concepts are and why we even want to unify them. But before we talk about unification though, let's take a little time to understand what quantum mechanics and general relativity really are. Can we go to the next slide, please? So yeah, quantum mechanics is the hot new science of the very small. It was developed in the 1900s to explain phenomena occurring at the scales of atoms and molecules. From its very origins, it has had a reputation of being extremely counterintuitive and difficult. Through the years, however, the theory has embraced its counterintuitive approach to reality to become the foundation of one of the two reigning theories of physics, quantum field theory. So I think it will help for us to know a bit about quantum mechanics, or QM for short, if we are to try to explore why quantum field theory doesn't agree with its partner, general relativity. And although the mathematics of quantum mechanics is as arcane as you can imagine, let's try to make some sense of its basic concepts as briefly as we can. Can we go to the next slide, please? And also, if you're curious, that photo was the Schrodinger's cat, just a joke. Yeah, never mind. To understand the basic oddities of quantum mechanics, let's look at the slide here. It's often useful to contrast it with the physics we already know, our everyday classical physics, like a car going down a road or throwing a ball up in the air. In classical physics, objects are described by a set of properties which are basically numbers. For instance, a ball thrown at an angle to the ground or a car racing down a track can be described by their position x or their velocity v or their acceleration a and so on. For every physical case we have, we can use the equations of motion we know. In this case, it would be F equal to ma. And then we can feed in the x and v numbers for the car or the ball, which we also already know, to get the x and v numbers for the body at some later time. Importantly, if we know them at one time, we can know them exactly at any other time. Next slide, please. Quantum mechanics works a little differently. In quantum mechanics, we don't start with the object's numbers, x or v. As you can see here, we instead start with something called a state. And you might also have heard of this being called as the wave function of the particle or of the body. This state can be obtained by solving something called the Schrodinger equation for our body, and it's just a black box which contains all of the information we need. As an aside, the Schrodinger equation is just the quantum mechanical equivalent of F equal to ma. Once we have the state of the system, we can get its properties x, v, m, and so on by feeding particular functions into the state. The existence of the state and what we feed into it is one of the big ways in which quantum mechanics is different than classical mechanics. In classical mechanics, the position, velocity, energy, and other properties of a body are just numbers. which we feed into our equations to get those numbers for a later time. In quantum mechanics, they are functions. And we need to feed these functions into the state to get back what we need. We would expect that we would get back numbers, x, v, and m, applying exactly to the body for any later time. But we don't actually get that. This is the second big difference between classical and quantum mechanics, which we are going to discuss now. Can you have the next slide, please? So we saw that quantum mechanics is weird about what we input into the state, but it is even more weird about what we get out of the state. So let's go back to the classical example of a car going down a road or just normal classical mechanics. What do we expect from classical mechanics is that if we put in the numbers for the position, velocity, and acceleration of a body at some time, we shall get back the numbers for those properties for any later time. It's pretty straightforward. I think we already know this. Most of us know this. An important feature here is that if we know the numbers for one point of time, our equations can give us the exact numbers for any other point of time without any doubt. Can you have the next slide, please? But again, quantum mechanics is very different in this regard. What we feed into the state with the functions corresponding to the position or the momentum and so on, once we do that, we don't get exact values for the position, velocity, and so on for some later time, but instead we get a probabilistic value. This means that if we repeat an experiment 100 times, we will get different results each time. And quantum mechanics can tell us the ratio of how many times we will get one result compared to the other. Or it can tell us the average value of all these measurements. And we can get these average values by using these functions and feeding them into the state. But we will never get one exact particular value for the position or the momentum or properties like this of the body. Actually, the fundamental principle here is quite shocking. It's not just that we don't know the exact position of the particle, and therefore, out of necessity, we can only talk about the probabilities. It's that the particle actually does not have a definite position at all. It's only when the particle interacts with something else, like our measuring instruments, that it decides where it should be. This sounds really confusing, and it's confused, I think, everyone who's ever studied this or worked on this. But at this point, we're pretty sure that that's how this works. And even more confusingly, the particle always makes this decision of which position it should find itself at according to the rules of quantum mechanics. Like it will only appear in one particular position that that number of times, so that the ratio of the amount of times it appears in that position as compared to some other position, that ratio follows the probabilities which we got from the theory of quantum mechanics. So this probability is all encoded in the quantum state. And I know this is quite a lot to take in. And Einstein himself, who was one of the fathers of quantum mechanics, he himself was troubled by this weirdness. So while you digest this for a bit, I'll let Dhruv tell you guys a bit more about the great work Einstein is most famous for, and I'll be happy to take any questions at the end.
All right. So, as Nachiket said, quantum mechanics is one of the areas of physics that just bewilders anyone who tries to study it. It's extremely counterintuitive. It makes no sense whatsoever. We know how it works, but we don't know why it works the way it does. We're extremely puzzled as to why that's so. But on the other hand, Einstein's theory of general relativity is regarded by many in the field of physics as one of the most beautiful and elegant theories of all time. And that's because Einstein himself was opposed to quantum mechanics. He didn't like the ugliness that came out of quantum mechanics. He didn't like the fact that particles can only be predicted to a certain extent. And there are only probabilities that we can look at, but we can't know for sure where a particle is or how fast it's moving. So let's look at general relativity. General relativity was Einstein's theory of gravity. And the interesting thing about gravity is that it is the one force that is solely responsible for how the universe looks like, how the universe is structured. And that's because as you zoom out to larger and larger scales, from the solar system to galaxy clusters, until you have the entire universe, all other forces become negligible. They all become really weak on large scales. And the only force that's left to dominate is gravity. So Einstein's theory isn't just a theory of gravity, it's a theory that describes the structure of the universe as a whole. So let's talk about that. Einstein's relativity was nothing short of a complete rebirth of physics. So let's really briefly go into the history of gravity. Isaac Newton, came out with his theory of gravity 400 years ago, and it was complete genius to everyone at the time because most of us, or a lot of us, would be familiar with the story that Newton saw an apple fall from a tree. It didn't really hit his head, but he did see an apple fall from a tree. And when he saw the apple falling, he related that falling apple to the moon orbiting the Earth. It was one of the greatest syntheses in the history of science at the time. No one could have ever imagined such a thought could occur. How can you relate a falling apple to the moon going around the Earth? He was a genius. And by the way, he did this when he was in his mid 20s. He was just a little older than many of us here. So he was a genius. But his law of gravity was not the whole story. This is where we have two branches of physics that we're going to contrast. One of them is called classical physics, and Nachiket talked about that in a bit. But the other theory, the other branch of physics, is what we call modern physics. Now, classical physics, as Nachiket outlined, describes situations that we see on an everyday basis. So it describes situations that we're all familiar with, like if you're talking about a race car going down the track, a moving car, a flying airplane, the moon going around the earth, an apple falling from a tree, a bouncing ball, etc. All situations that we can observe with our very eyes and situations that we're familiar with. That's what we call classical physics. And Newton's laws work pretty well in the realm of classical physics. They were renowned by many for hundreds of years until modern physics came along in the 18th and 19th centuries. And this is where Einstein comes in. Einstein published 5 revolutionary scientific papers in 1905, and 2 of these papers were on special and general relativity, the 2 theories that we're going to focus on right now. Special relativity we're not going to go into that in detail. We're going to focus on general relativity, but special relativity deals with time dilation. The essence of special relativity, and again, this is also completely counterintuitive, and if you hear this for the first time, it's going to bewilder you. Special relativity says that the faster you travel, and I don't mean as fast as a train or as an airplane, I mean really fast, like speeds that are close to the speed of light. The faster you travel, the slower time passes for you. And let that sink in for just a moment because that is extremely counterintuitive. Newton believed that across the universe, time beats at the same rate. 1 second passing by on Earth is the same as 1 second passing by on Mars or in a different galaxy. But Einstein said, no, that's not true. So, for example, let's look at 2 people. Suppose we have 2 twins that are exactly the same age. And let's put one of them in a rocket. This is a hypothetical thought experiment. Let's put one of them in a rocket and send them up into space. And let's keep the other twin on Earth. And again, they're the same age when we start off with them. Now, the one that we put in a rocket and send off into space, let's make that rocket travel really fast, close to the speed of light. And let's have that twin come down back to Earth after traveling really fast for a few years. Now, in the mind of the observer, a few years has passed. But in reality, time has passed by much slower for them than for the person who stayed back on Earth. Again, this is counterintuitive, but bear with me. Time passes slower for the person in the rocket. And so they age less compared to the person who stays back on Earth. So, what I'm saying is that when you have these 2 people meet back on Earth again later on, one of them is going to be many years older, and the other is going to be just a few months, maybe even just a few days older. That's special relativity. That's time dilation. And that's extremely counterintuitive. And it's shocking when you hear about it for the first time. But that is how things really are. Time does not beat absolutely throughout the universe as Newton thought it does. Newton was wrong with respect to that. Einstein was right. Time is relative. Time is not absolute. But that's special relativity. Special relativity didn't account for the theory of gravity. That was where general relativity came along. So let's take a look at that. General relativity was what Einstein described as the happiest thought of his life. Again, Newton's laws don't tell the whole story when it comes to modern physics. Modern physics, if we're also looking at completely extreme situations like near a black hole or near a neutron star, where the gravity is so strong that absolutely nothing, not even light, can escape, Newton's law of gravity doesn't work entirely. Einstein's theory of general relativity has to come in. So, how does it work? Well, we think of gravity in everyday life as an invisible force. If I throw a rock off the edge of a cliff, it's going to land in the ocean. If I jump, I'm going to fall back down. And we don't see the force that is doing this. We see gravity as an invisible force. But Einstein was a genius, obviously, and he saw gravity in a completely different way. The essence of general relativity is that the presence of mass or energy curves space time. Now, what does this mean? Let's do a thought experiment. Let's say I have a bowling ball, a trampoline, and a marble. Now, let's say the bowling ball represents the sun. The sun is our nearest star, and it's much larger and much heavier than the Earth. So let's say the sun is our bowling ball, and let's say the Earth is our marble. And let's say the trampoline represents the fabric of space time. Now let's put the bowling ball on the trampoline. Because the trampoline is made of a flexible material, it's stretchy and it bends, what's going to happen? Obviously, because of the weight of the bowling ball, the trampoline is going to bend downwards as you put the bowling ball on it. And now, if you shoot the marble along the trampoline, what's going to happen is because the trampoline is bending because of the weight of the bowling ball, the marble is going to go around the bowling ball when the trampoline is bent. And that is an analogy that outlines the theory of general relativity. The marble is the Earth, the bowling ball is the sun, the trampoline is the fabric of space time. So the fabric of space-time is bent by the presence of a very heavy mass like the sun or a black hole. And when you have a lighter mass on that trampoline, like the Earth, it's what causes the Earth to go around the sun. So that's how Einstein envisioned gravity. If you think about it, then gravity, according to Einstein, wasn't really a force at all. It was just the result of the nature of space-time itself. If you place a heavy mass on space-time, it's going to bend, and gravity is the result. It's not a force, it's a manifestation of the bending of space-time. So that was how general relativity came about. And again, it was completely counterintuitive at the time. Nobody saw this, but when they realized what Einstein was saying, they were at his feet because it was complete genius. No one had ever thought of envisioning gravity in this way. So that's general relativity in a nutshell. Now let's talk about unification. And before we talk about unification, it's worth mentioning again, we want to emphasize as much as possible that quantum mechanics and general relativity are two extremely powerful theories that have been tested as much as possible. Quantum mechanics has been probed by physicists as much as possible, and so far it's given us results that make sense. General relativity, too. We've done as many tests of general relativity as possible, and Einstein has never shown to be wrong. And yet, the shocking thing is, as we're about to see, at least one, if not both, of these theories has to be wrong. So, why is that? Let's talk about unification. Let's talk about why it's necessary to combine these two theories together. Now, we have to introduce what we call the fundamental forces at this point. There are four forces in the universe that every other force can be traced back to. These four forces are what we call gravity, electricity and magnetism, and the weak and strong interactions. We're all familiar with gravity, of course. Electricity and magnetism, now these were at first thought to be two different forces, but actually it turns out they're different manifestations of the same force, and we call that force electromagnetism, the electromagnetic force. The weak and strong interactions are two different forces that work on an extremely small scale. So they're part of quantum mechanics. They describe the behavior of atoms and molecules under certain conditions. And it turns out that all four of these forces can be described by what we call field equations. They're subject to fields. Gravity works in a gravitational field. Electromagnetism works in electric and magnetic fields. So the field equations for gravity are the Einstein field equations. Those are basically the foundational equations for general relativity as a whole, the theory as a whole. For electromagnetism, we have Maxwell's equations, and Maxwell's equations are a set of mathematical equations that form the basis of all electric and magnetic forces. And for the weak and strong interactions, we have what we call Yang-Mills equations. So these are the set of equations that we have for each of these four forces. And we have what we call the Standard Model. The Standard Model is a framework in particle physics that assigns a particle to each of these four forces. And for the strong interaction, you have what we call a gluon. That's a particle that we assign to the force. For electromagnetism, we have what we call a photon. A photon is basically a particle of light. But for gravity, gravity is where the standard model breaks down. Gravity is the odd one out. The standard model hasn't been able to find a particle to assign to gravity yet. We call it the graviton, but it's still a hypothetical particle because we haven't been able to find any such particle yet. And so Einstein's field equations stand out from all three other forces. We've essentially been able to largely combine the other three forces together, but gravity is the odd one out. We haven't been able to reconcile general relativity with all these other forces. And to make things a bit more clear, because this is quite broad, we're going to give you a specific example where gravity fails to match quantum mechanics. And that's what we call the firewall paradox. Nachiket's going to talk about that in a bit.
Hey guys, so we sort of miscalculated with time. So I'm sorry if this seems too brief or too confusing. It is equally confusing for us, to be honest. But let's go over what the firewall paradox actually is. So it starts with Hawking. I think a lot of us know why Stephen Hawking is famous. He published a paper which theorized that black holes can actually evaporate. And the way they evaporate is by having two entangled particles pop into existence just outside the event horizon. Entanglement basically means that their states are mixed for now. That's all it means. And once they pop into existence, one of them goes into the black hole and the other leaves, and the other is lost forever. And for someone outside the black hole, this looks as if the black hole is actually emitting that particle. And this emission causes a loss in mass, and slowly the mass of the black hole goes down and down. And finally, the black hole completely evaporates. But if the black hole evaporates, what happened to what we threw in there? So if we throw something in and then the black hole evaporated 20,000 years later, the information about what we threw in is lost forever. But this is not allowed in quantum mechanics. It's a very important principle called unitarity, which means no information is ever lost in this universe. So we need a way to conserve this information. And one solution which was brought up is that the particle which the black hole emits, it actually contains the information of what is already inside the black hole. So for this to happen, this emitted particle must also be entangled with the particles which have already been emitted and are at some far away distance. So the emitted particle is entangled with particles emitted before it. However, and can we go to the next slide, please? Oops. Yeah, however, we know that this particle, which I denoted as state 2 there, that particle is also entangled with the particle which is going inside, right? So it is entangled with both the particle which already left and the particle which just went in. This is not allowed in quantum mechanics. And if you can go to the next slide, quantum mechanics does not allow one particle to be entangled with two particles. So one of the entanglements have to break. This breakage releases energy, and this energy is so great that this creates a giant sort of firewall around the black hole. Anything which enters the black hole, even before it enters, it will be completely fried by the firewall. But this is where general relativity raises a question, because general relativity says that the outside of a black hole, the space-time outside of the black hole is no different from space-time anywhere else. So technically, if you were in a completely windowless spaceship and you were entering a black hole and there were no tidal effects, you would not be able to tell when you entered the black hole. But if there is a firewall, obviously you can tell because you can feel the heat and you can feel the pain all over your body as you die to the fire of the firewall. So what's going wrong here? Can we go to the next slide? Yeah, no one actually knows what is actually going wrong here. And there are some interesting proposals. If you're curious about it, you can Google something called ER equal to EPR, which proposes that the emitted particle and the inside of the black hole are actually connected by wormholes, and it's actually pretty fascinating. But yeah, it's all pure hypothesis at this point. So actually no one knows. So maybe it's a problem for us to solve. And until we solve it, this will remain one question which waits for scientists to unify quantum mechanics and general relativity for us to be able to answer.
So that's essentially it. We hope you guys enjoyed this talk. We hope you guys got a bit out of what we were talking about for quantum mechanics and general relativity. Again, just to recap, the essence is that these two theories are extremely powerful and describe a wide range of phenomena that we can observe, but one of them has to be wrong, if not both. And the question is, which one is it? And will we ever be able to find a theory that accounts for both of these theories and encompasses them as a whole, a final theory, a theory of everything? Thank you.
And we'll just take a few quick questions. I'll try to answer all the questions pertaining to my part of the talk. So I'll go real quick. A asks, what do you mean by information? Isn't it the item itself? It's not actually the item itself. You can imagine it like, so if you have a book, the book contains information. So if you burn the book, you would think that the information is lost, but theoretically, and this is completely theoretical, theoretically you could take in all the molecules of carbon dioxide and all the molecules of sulfur which were emitted by the book. You could put them back together and you could, in theory, completely recreate the book. So that's what we mean by information, that that we can rearrange something to bring it back to what it originally was. This is a very bad description of it, but it sort of makes sense. So that's what we mean by information. And to continue, um, so does the object that was sucked into the black hole gets evaporated with the black hole, asked by anonymous attendee? And yeah, the object which was sucked into the black hole becomes a part of the black hole. So now it has no separate identity than the black hole. And if the black hole gets evaporated, that object also gets evaporated, which means uh, now there is no theoretical way to take bits and pieces of the black hole and rearrange them and do some magic with them and recreate that object. So that's what we mean by information being lost. Bernard asks, are there any experiments planned or proposed to resolve this conflict? The problem is that we don't really have access to black holes either experimentally or observationally. We can't send a spaceship to a black hole because all of them are too far away. So that's where we are right now. We just don't have the resources to be able to experimentally answer this question. Another anonymous attendee asks, in quantum mechanics, can you say that a particle doesn't have a position until you measure it, or can you only say that we don't know what is going on before we measure? If you get philosophical about it, we can say that there might not be a difference between those two statements, but this is actually a philosophical question because physics deals with what we can observe. So what is happening when we cannot observe it is sort of a shaky ground for physics. And there are lots of philosophical interpretations of quantum mechanics, but the ones which we are usually taught, it's called the Copenhagen interpretation, which says that yes, until we measure it, the particle doesn't actually have a position. And I think I'm going to pass it on to Dhruv now. I'm really sorry if I could not answer all of your questions. I'm going to let Dhruv answer some of your questions now.
Yeah, Nachikit, could you just see if there are any questions related to what I spoke about? Because I can't see the chat.
Oh, um, uh, one question is, why does time pass slower for the other twin? I think this relates to the twin paradox.
Yeah, so that's a result of the mathematical equations that describe special relativity. The math just works out so that the faster you travel, the slower time passes. Um, I can't really answer that verbally because it's all in the math, but in essence, special relativity does describe it that way. I'm sorry if that didn't answer your question, but essentially it's the mathematical equations that tell you how time passes slower for you.
The one more question is, oops, I'm sorry, even I can't see a lot of the. Yeah, I don't see any other questions for this part. I'm really sorry if I missed a few questions. I tried to answer a few in the chat, but we really need a time for the other team to begin preparation for their talk. So I'm really sorry that we overshot on time. We'll try to be more disciplined about it for the next time. Thank you so much for attending, guys. It was a
Thank
real
you.
pleasure. And yeah, I hope to see you all for the next time the Bay Area Science Festival takes place, whether remotely or in person.
Take care, everyone. Stay safe
Yeah.
during these challenging times. Thank you again.